chapter in the course on sequences and series of functions. Okay, so some of these ideas may be familiar to you, and we have certainly talked about very briefly sequences of functions when we talked about power series earlier in the course. So let me begin by perhaps the most naive and simplest definition of convergence of a sequence of functions. Right. So the sequence Fn of real valued functions that are defined on some subset S of R converges pointwise to some limit f if the following is true. Okay, so this is fairly straightforward. You have a sequence of functions fn which are all defined, let's say, on some common domain S, which is a subset of R. We say that this sequence of functions converges pointwise to another function f, which also of course has to be defined on S, if at every x lying in S, the sequence fn of x, remember this is a real valued sequence fn of x, right? As n tends to infinity, this sequence must converge to the value of f at x, right? That's why the name pointwise, because at every point this sequence of functions converges to the value of the limit function at that point. Okay, so we often write familiar notation, limit n tends to infinity, fn is equal to f, or fn right arrow f, to indicate this type of convergence. Okay, so let me remind you that pointwise convergence is actually something that one has already encountered in the context of power series. So let me just remind you what that looked like. So note, we have encountered pointwise convergence in the context of power series. So if you had a power series of this form, summation an x raised to n, so we already said that if you look at the sequence of running sums, right, for any x, you look at the sequence of running sums, we know that this sequence converges for mod x less than r, which, if you recall, is the radius of convergence, right? And we interpret the pointwise limit of this sequence of functions as the power series. Right? So the point here is that the power series was in fact defined as the pointwise limit of this sequence of functions. It's actually a series, but we know that series can also be thought of as sequences, right? So the sequence of these running sums of functions the pointwise limit of this, which is guaranteed to exist for mod x less than r, is exactly what we interpreted as the power series, right? So that's an example of pointwise convergence that one has already encountered. Now, the first question we are going to ask in the context of pointwise convergence is the following. That is, if I know some structural information about the sequence of functions fn, can I infer something about the structural properties of the limit function? Right? In particular, our first question is going to be about continuity. So if fn converges to f, where each of these functions is continuous, is f also continuous? Right? So what we are asking is, if you have a pointwise limit of continuous functions, is the limit also continuous? Right? And the answer, as we will give an example to demonstrate, is not necessarily. Right? So it is in fact possible for a sequence of functions, a sequence of continuous functions, to actually have a pointwise limit which is discontinuous. Okay, so let's illustrate that via this example. So suppose you define the sequence of functions fn of x as follows. Fn of x is equal to 1 minus, let's say, mod x whole raised to n. Okay, and s in this case, the domain of all of these functions is, let's say, from -1 to 1. All right. Now it's easy enough to figure out what is the, shall we say, pointwise limit of this. So if you look at the limit of fn of x as n tends to infinity, well, you will see that for x is equal to 0, then this is just a constant sequence, right? Fn of 0 is equal to 1, and so the limit must also be 1, corresponding to x equals 0. For x not equal to 0, 1 minus, and noting that x lies in the open interval from -1 to 1, 1 minus mod x raised to n is therefore exponentially decaying, right? Because 1 minus mod x has an absolute value that is strictly less than 1, and so it will decay exponentially to 0. All right. So in this case, you do have a pointwise limit, but the pointwise limit is obviously discontinuous, right? It is 0 everywhere other than the origin. At the origin, it is equal to 1, right? So each of the fn's is continuous, but pointwise limit is not. Right? For those of you who are from electrical engineering backgrounds, you would also have seen examples of these in the context of, say, Fourier series and so on, right? Where the functions that you use in your Fourier series expansion are all, very, very smooth, but it is possible for discontinuous functions to also emerge as the pointwise limit of such sequences, right? Which is to say that even discontinuous functions can in fact be represented via a Fourier series. All right. So that is our first example. And so since we know that the pointwise limit of continuous functions is not necessarily continuous, the next natural question to ask is there more a stronger notion of convergence which actually will ensure that limits of continuous functions are in fact continuous? So is there a stronger condition that ensures this? Ensures that the limit continuous sequence are continuous. Right? And it turns out that that is in fact the case, as we will prove later. in this video that the notion of uniform convergence is in fact that notion of convergence which in fact guarantees this property that limits of continuous functions are continuous. Okay, so first let us begin by defining what uniform convergence means. So once again, let Fn be a sequence of functions on S, which is a subset of R. So we say that Fn tends to F uniformly as opposed to pointwise before on S if the following condition is satisfied. Given any epsilon greater than 0, there exists a knot such that Fn of x minus f of x is less than epsilon for all x in S and n greater than n naught. Okay, so that's your definition of uniform convergence. Now, why is this uniform convergence? Because for any epsilon, there exists an n naught such that the deviation between Fn of x and f of x has to be less than epsilon for every x and for every n greater than n naught. So the point here is that the n naught is not allowed to depend on x, unlike in the case of pointwise convergence, where you are looking for the sequence Fn of x to converge to f of x at every point x, but therefore the n naught, the point beyond which Fn of x becomes close to f of x, can depend on the location, right? Can depend on x. Here that location dependence is basically removed. So which means that n naught cannot depend on the location, that there should be an n naught such that across all locations, in other words across all x, Fn of x should be within an epsilon distance of f of x, okay, for large enough n. Okay, so that is why this is a stronger notion. Okay, so a couple of immediate takeaways. So in the definition, n naught is not allowed to depend on x. Right, and another thing to note is that uniform convergence implies pointwise convergence. So it is in fact a stronger notion of convergence. Right? So if you have a sequence of functions which is uniformly convergent to a certain limit, then it is also pointwise convergent. Right? Another way of telling saying the same thing is that if you want to check for uniform convergence, it suffices to first check for pointwise convergence and then evaluate that particular candidate limit for whether or not uniform convergence occurs to that limit or not. Right? So the only candidate for the limit of a sequence of functions for under uniform convergence is in fact the pointwise limit if it exists. So if the pointwise limit doesn't exist, you know that the sequence of functions cannot be uniformly convergent. And if the pointwise limit exists, then indeed you can check whether that pointwise limit also satisfies uniform convergence or not. All right. Let's do another, shall we say, graphical interpretation of this definition. So suppose that this limit f looks like this. All right. What this tells you is that if you fix any epsilon, right, then the functions Fn of x have to be within a certain strip of width epsilon around this limit, right? So if I now plot, let's say f plus epsilon and f minus epsilon, then the point is that beyond n naught, the function f of fn of x has to lie completely within this strip. So fn of x lies within this strip for n greater than n naught. Right? So that is the, shall we say, the graphical way of interpreting uniform convergence. Right? So epsilon can be thought of as basically defining a strip around the limit function, and the curves of the sequence of functions fn of x must all lie within the strip for large enough n, right? So as you make the strip smaller and smaller, the n naught will increase, but the point is still that uniform convergence requires that beyond a certain point all functions must lie entirely within the strip. All right, so that's the definition of uniform convergence. Before we prove what we had already said, namely that uniform convergence implies that limits of continuous functions are continuous, let's actually first do a few examples. So the first example we will consider is in fact the same example we used for the pointwise limit, so which is fn of x is equal to 1 minus mod x raised to n. Again, x from -1 to 1. Okay, we already know what the pointwise limit is. What I want to show here is that this sequence of functions does not in fact converge uniformly to its pointwise limit. So remember that fn tends to f, which is defined as 1 for x is equal to 0, 0 for x not equal to 0 pointwise. So what you're going to do is show that fn does not in fact converge to f uniformly. Right? How do we do this? We will prove this by contradiction. So assume the contrary. That is, assume that you do have fn converging to f uniformly. In that case, setting epsilon equals, let's say, half, that would imply that there exists an n naught such that, well, the difference between the function, that is 1 minus mod x the whole raised to n, this the difference between this and the limit. So let's just look at the limit at points which are different from 0. So in that case the limit is going to be 0. This must in fact be less than half for all x in, let's say, -1 to 1 minus the origin, and for n greater than n naught. Okay, so suppose I specialize this to only, let's say, the positive half of this, right? The open interval from 0 to 1. What that would imply is that 1 minus x raised to n must in fact be less than half for all x in the interval from 0 to 1 and, let's say, n greater than n naught. Okay. However, this condition cannot be true when x is sufficiently close to 0, right? Because if you look at this, this function as x gets close to 0 will in fact approach 1. So this is not true. So this gets, no matter what n naught you pick, right? This condition will in fact be violated as x approaches 0. This is not true for x close to 0, right? I'm not going to say that very formally, but I think that's obvious, right? No matter what n naught you choose, at n naught plus 1, when x is sufficiently close to 1, it must be that this condition is violated, right? So that gives us the contradiction. right? So that argues therefore that uh, this example where we had pointwise convergence of a sequence of continuous functions uh, to a discontinuous limit, uh, in that particular example you don't have uniform convergence, right? This is just to contrast the definitions between the pointwise convergence and uniform convergence, right? Let's do a couple of more quick examples. So suppose I look at fn of x, which is defined as sine of nx upon n. All right, so I leave it for you. Again, you can take the domain to be whatever you like. Let's say x in R. In this case, show that fn of x in fact converges to 0 uniformly. Okay, so I leave it as an exercise to you to show this. To give you another example where you in fact don't have uniform convergence, let's look at this example. Fn of x is equal to n times x raised to n, where x belongs to this interval. It's the interval from 0 to 1 where 0 is included but 1 is excluded. Okay, so again I leave it to you to check that fn of x in fact converges to 0, the function that is identically 0 pointwise but not uniformly. Right, so again I leave this as an exercise for you to show using very similar ideas to what we did in the first example above. One can show that in fact this convergence happens pointwise but not uniformly. Alright, so having done the definition of pointwise convergence, the definition of uniform convergence, and seeing some examples of both of these, now let us prove the claim that I had made earlier, namely that the uniform limit of continuous functions is continuous. The uniform limit of continuous functions is continuous. Okay, I've written this in kind of short form. In long form, the statement of the theorem would be as follows. Right? Let Fn be a sequence of functions on S, which is a subset of R, and say Fn converges to F uniformly on S, now if each Fn is continuous, then F is continuous. Rather, we'll actually make it a little bit more precise. If each Fn is continuous, let's say at x0, then F is continuous at x0. Alright, so yeah, we are not even talking about continuity over the entire domain. We are proving something even stronger, that if you can just argue that every function is continuous at some x0, then the limit must also be continuous at that x0. So x0. Okay, so that's the statement. Now let us go through the proof. So this is actually a fairly elementary proof, but this idea of the proof actually is used all over the place. So this type of idea of the proof is typically called the epsilon by 3 argument. Right, and we'll see why. Alright, so what we're going to do is we have to argue the continuity of the limit at x0. Right, so therefore we have to look at this difference f of x minus f of x naught, right? And argue that so long as x is sufficiently close to x naught, this difference between the function value at x and the function value of x naught is well at most epsilon, right? That is how one would argue continuity of this. Now what we are going to do is break this up into 3 chunks and show that each of those chunks is less than epsilon by 3, right? Hence the name epsilon by 3 argument. So this is less than equal to, let's say, f of x minus fn of x, right, plus fn of x minus fn of x naught plus fn of x naught minus f of x naught. Okay, you just have to add and subtract fn of x and fn of x naught and then use the triangle inequality to come to this. Okay, so the point is that the left hand side does not depend on fn, it depends only on it depends only on f, but we have broken it up into 3 pieces. The first piece concerns the difference between f of x and fn of x, right, which from the statement of uniform convergence we can show is small. The third term is again the gap between fn of x naught and f of x naught. Again, this is small because fn converges to x. And the second piece, fn of x minus fn of x naught, we will see that that is small because of the fact that the function fn is continuous, right? So the first and the third term is small because of the convergence, and the second term is small because of the continuity of fn itself at x naught. All right, so let's make this formal. Given epsilon greater than 0, we know that there exists a capital N such that mod of fn of y minus f of y is in fact less than epsilon by 3 for all n greater than capital N. Yeah, so this follows from the fact that, so this is true for all y, right? For all n greater than n and for all y in S, right? So I can in particular apply this to the first term and the third term in the breakup above, right? Because this is true for all y in the domain and for all n greater than capital N, right? Now what I'm going to do is pick a particular value of n. So since f capital N plus 1, right, of x is continuous at x naught, right, there exists a delta greater than 0 such that if x is within a delta distance from x naught, that would imply that f n plus 1 of x minus fn plus 1 of x naught is going to be less than epsilon by 3. Right, so now we have all the pieces required. So for x such that it is within a delta distance from x naught, if I now go back and evaluate the difference between f of x and f of x naught, all right, so let me just rewrite those 3 terms and then we'll see how each of those 3 terms is less than epsilon by 3. So I write it as f of x minus f capital N plus 1 of x plus f capital N plus 1 of x minus f capital N plus 1 of x naught plus, well, f capital N plus 1 of x naught minus f of x naught. Okay, now because of this condition, right, the first and the third term must be less than epsilon by 3. Right, in one case you're just setting y to be x, in the other case you're setting y to be x naught. All right, and the second term is in fact less than epsilon by 3 by this condition. Right, so overall you are less than epsilon, right, and that completes the proof. Why? Because what you have demonstrated is that for any epsilon I can come up with a delta such that if x lies within a delta distance of x naught, then for the limit function f, mod of f of x minus f of x naught is in fact less than epsilon, right? So that completes the argument that the uniform limit of continuous functions is continuous. All right. So before we conclude, there is one final uh, interpretation of uniform convergence that we will study, and that is the following. So uniform convergence can also be stated as follows. All right, given epsilon greater than 0, there exists n such that if you look at the supremum of the difference right, where the supremum is overall x belonging to S, this supremum must be less than epsilon for all n greater than capital N, right? Go back to the definition of uniform convergence and convince yourself that this is in fact exactly the case, right? In fact, this was the main idea behind that graphical interpretation of uniform convergence, right? For any epsilon, there exists a capital N such that for all n greater than n, if you look at the supremum of the differences or the supremum of the error between the limit and Fn, that supremum of the error across the entire domain must be less than epsilon, right? So you can bound the supremum of the gap between Fn of x and f of x by epsilon for n sufficiently large, right? So this is in fact equivalent to the definition of uniform convergence. And now if you stare at this, you should be able to convince yourself that this is in fact also equivalent to saying that if you look at the limit as n tends to infinity of this difference, the supremum of the set of these differences, Fn of x minus f of x, where x belongs to S, this limit is equal to 0. Why? Because this function, now this is a sequence, right? This is a sequence in n. Right? What we have exactly said is that given epsilon greater than 0, there exists a capital N such that for all n greater than capital N, the values of this sequence will become less than epsilon. Right? So this is yet another very nice way of thinking about uniform convergence, namely that the limit of the supremum of the error between Fn of x and f of x, where the supremum is being taken over, all elements of the domain, this supremum of the error must in fact tend to 0 as n tends to infinity, right? So that's equivalent to uniform convergence. Now, this interpretation can also be used sometimes to either demonstrate or to disprove uniform convergence, right? So let's do one example to illustrate this. Let us say that Fn of x is defined as follows: n square into x raised to n times 1 minus x, right? And in this case, the domain is the closed interval from 0 to 1. All right. Now, if I want to check for uniform convergence, note that I will first check for pointwise convergence and then check whether that pointwise limit is in fact also whether the sequence converges uniformly to that pointwise limit, right? So the pointwise limit is actually quite straightforward to check. So I leave it to you, in fact, to just check that Fn of x in fact converges to 0 pointwise. So I want to check whether or not the convergence to 0 is also uniform, right? If the convergence to 0 is uniform, note that this is a non-negative function. if I use this interpretation that we have just written above, that is the supremum of the difference between the function and its limit must be 0, what that means is that the maximum of fn of x must in fact converge to 0 as n tends to infinity, because it is at the maximum of fn of x that you will have the maximum, the supremum of the deviation between fn of x and f of x. Okay, so what we will do is let us maximize fn of x over the interval 0 to 1. Okay, and except at the endpoints, note that the function is positive. Okay, so it is going to have a maximum. Clearly, it's a continuous function, it's going to have a maximum. Now, since it's going to have a maximum, we know that the derivative at that point is going to be 0 because the function is also differentiable, right? So therefore, one way of looking for that maximum is in fact to simply set the derivative of fn to 0. Okay, I leave the algebra to you to show that setting the derivative of fn to 0 corresponds to basically saying that n square into n into x raised to n minus 1 times 1 minus x is equal to n square into x raised to n. Okay, so you can massage this and show that in fact the value of x at which the derivative is 0 is in fact given by n plus 1. Okay, so I claim that x star, which is n divided by n plus 1, is a maximum. Is a maxima, let's say. Okay, why do I claim this? Well, I know that the function will in fact attain a maximum. We know that that maximum is going to be positive, and we know that the derivative must be 0, but the only point between 0 and 1 where the derivative is 0 is in fact n by n plus 1, and so therefore n by n plus 1 should in fact be the point where the function attains its maximum. So if I want to understand the maximum deviation from the pointwise limit 0, all I have to do is evaluate fn at this point, right? So therefore, if you look at the soup of fn of x, right? So this is in fact the difference between fn of x and its pointwise limit, right? Over x running from 0 to 1. Well, this is in fact simply going to be fn evaluated at x star, which is n by n plus 1. Okay, which again, after a bit of substitution, can be shown to be n square by n plus 1 upon 1 plus 1 by n, the whole raised to n. Alright, we know that the denominator tends to e and the numerator tends to infinity. So it's easy to see that this in fact will tend to infinity as n tends to infinity. Alright, and so since this sequence does not converge to 0, we know that you don't have uniform convergence. So since the error, if you will, the soup error between fn and the pointwise limit in fact tends to infinity, mind you, you still have pointwise convergence, yet the supremum of the error actually pushes off to infinity, right? So this implies that the convergence is not uniform. Right, that completes this example. We will continue our exploration of limits of sequences of functions in the next video.